Toon shading is. Toon shading is when cartoonists use solid colors that don't vary in regards to materials. The part of the character that needs shading will most often be colored a darker version of the main material color. This in the end adds lighting cues to the shape and context of the character in the scene. As you can see here on the monkey, his cheekbones look hollow as they have been colored a darker tone than the rest of his face. Toon shading is hereby a style of computer rendering that replaces the natural gradient of conventional 3D rendered objects and converts them into flat colors and harsh shadows.
Looking back at why toon shading was first created, the shader has mainly been used in two industries, in film and in computer games. According to Cooper, who is an art historian, the shading was first introduced in films. The main reason behind creating a toon shader in films was to automate the traditional process of generating hand-drawn images. The traditional method of achieving the effects of a toon shader was to hire artists that would hand-draw images. The process of creating these effects was hereby made more efficient by introducing computers and shaders to the film industry, as seen in The Iron Giant from 1999. Looking at an article published in 2012 by Will Wise, toon shading has also been frequently used in video games, and the technique does not have one specific creator. In 1994, a game called Dr. Hauser used what seemed like a toon shader to give the characters in the game a much more 2D look. As we can see on the image, toon shading was still very new, which is why the shader is, for example, missing an outline. Since the first breakthrough of toon shading, the demands in regards to how the images produced by toon shading has changed immensely. Where it in the early years was required that the toon shader produced images with very little detail, it is now required that the shaders produce images that are much more realistic yet appear 2D. An example can be the game Borderlands from 2012. It is clear that the main use of toon shading has been to render non-photorealistic images and 3D objects, that in the end allows more complex scenes to be created. The computer allowed these complex scenes containing thousands of characters and objects to be rendered quicker and to be cost efficient.
In order to achieve a cartoonist look, it is required that the toon shader consists of three main areas. The three main areas in toon shading are highlights, shadows, and outlines according to Decaudy. Starting off with the highlights. The highlights are used to provide visual feedback in regards to the material type of an object and corresponds to the reflection of the light source, as we can see on the coffee machine. In addition to this, as toon shading is composed of flat colors, the images come out looking 2D. In order to add depth to the image such that they look 3D, toon shaders use shadows. In the article Stylized Rendering Techniques for Scalable Real-Time 3D Animations published by Carl Marshall, the boundary between a shadow and an illuminated area is a hard edge that follows the contours of the character. This edge is called hard shading. As a toon shader needs to convert diffuse lighting from many shades of colors into just a few colors, the system introduced in the article finds a transition boundary and shades each side of the boundary with a solid color. Depending on where each side is according to the light, the side will be colored in a bright or dark color. One way to look at it is for where the light hits the object, the pixel will have a color value of 0, and where the shadow is, the pixel will have a color value of 1. A way to do this is by arranging all values into two ranges. All values between 0 and 0.5 become 0, and all values between 0.5 and 1 will be represented by 1. The result will be two colors, one for the light and one for the shadows. The math behind this is called a step function, which is what many state-of-the-art articles, including Marshall, use to create shadows and highlights. Normally, functions have a continuous range of values, as we can see on the graph to the left, but step functions only have two. At each frame, the dot product between L, which is the unit vector from the light source to the vertex, and N, which is the unit vector normal to the surface at the vertex, is calculated. As max L dot N crosses 0.5, the index into the texture map chooses a different color.
This method is used frequently when it comes to the highlights and shadows of toon shading. That being said, this method creates jagged edges between the transition line of a highlighted area and an area that is in the shadows and creates unwanted details. A more recent way of sharply separating shadows and highlights was implemented by Gulbrandsen. Gulbrandsen presents a solution to Marshall's problem of when you separate a diffuse surface into a light and dark side, it often results in unwanted details as seen in the image. In order to avoid this problem, Marshall suggests creating a shell which covers the actual geometry of the figure. He then stores the shell normals in a point cloud. The surface shader then samples the point cloud and calculates the normal, which is then used as the new shading normal, and this can be seen in the image. Opposite Gulbrandsen, who is trying to minimize the amount of details in the shadows, 5 researchers from Korea made an article called Detail Adaptive Toon Shading using saliency. They addressed the problem of not having enough details in the shadows of their model. They suggest a method of adjusting local contrast corresponding to the degree of visual importance of an area by using virtual local lights and adjusting the shading level according to the visual importance of an area by using the toon texture. As you can see on the left side of the image, we see a normal 3D rendered hand, and in the middle we see a regular toon shader. To the right we see the shader made with the technique from the Korean researchers. Here we see a nice blend between the two traditional shaders. The third important area in the toon shading is outlines. In order to give the 3D object a 2D look, the toon shaders most often implement an outline that lines the object. This in the end helps in separating the object from the background as well as giving it the feel of cartoons. To outline objects, one needs to find pixels that lie on the object's silhouette and color them with the outline color, which is normally black. An easy way of finding the silhouette is to use n.v as a measuring stick. Just as n.l measures how much light a surface receives, n.v calculates how much surface is visible from the current viewpoint. A point is visible when the result of n.v is positive and hidden when n.v is negative. Points at which n.v is close to 0 represents the transition from visible to hidden, and these are the points on or close to an object's silhouette. Looking at the state of the art, the problem in toon shading is not creating an outline, but it is to control the outline. And as can be seen in the image, we here have a snippet of code which calculates the edge color.
Looking at the outline of a toon shader, and more specifically the toon shader in Unity, the outline of the shader is not consistent. The outline becomes larger as the camera zooms out, and the hard line between the highlight and the shadow is very smoothed and not as harsh as seen in more recent toon shaders. As also mentioned before, the barrier between the highlight and the shadow has to be really harsh in order for the shader to have a proper cartoonish look. As seen here, Unity shader has all the components of a toon shader being an outline, a shadow, and a highlight. That being said, the transitional line between the highlight and the shadow is what looks like very blurry. Here we have an example of Unity's standard toon shader. This one is the one called Toon Basic Outline and takes care of the outline of the object. This shader works together with the basic Toon shader, which is controlling the shadow and highlight on the object. The material used on the sphere is also called Basic Toon Outline and is also a default material in Unity. If we start looking at the code, the first thing we see are the properties. We have a color, a texture, and other variables connected to the mesh. These properties will be shown in the inspector in Unity under Basic Toon Outline, and we can from there change things like outline color and so forth. This applies to all shaders. Every property in here is also sorted and can be accessed wherever and is seen as material data. Scrolling further down, we see our uniforms. We have two uniforms in this code, the first being outline and the second being outline color. These are variables whose values are consistent over the shaded surface. The next thing we see is our struct. We have two structs and they act like classes and hold variables for the objects. The first is the struct app data. Here we have the vertex position as a 4D vector and the vertex normal as a 3D vector. The second struct is the v2f struct. Here we set the clip space position output, and this struct basically creates a struct member to hold the coordinates for the fog, which will be used later, and it also holds a color.
Now we come to the vertex shader. Here we transform vertex position from object space into so-called clip space, which is what's used by the GPU to rasterize the object on screen. We also pass the input texture coordinate unmodified to the fragment shader. The vertex shader runs on every vertex of the 3D model. At line 30, we multiply the model view projection matrix with our vertex position and store it in o.position, and the model view projection matrix is built-in function in Unity. Then on the next line, we normalize the normal by multiplying the current model view matrix with the vertex normal and then transforms the view to projection. In other words, this is where we move the vertices along their normal vectors. From line 35 to 45, we calculate the outline of the model and calculate the fog coordinates and then stores them in the struct v2f. Now we come to the fragment shader. The fragment shader is a program that runs on each and every pixel in the object occupies on screen and is usually used to calculate and output the color of each pixel. Usually there are millions of pixels on the screen and the fragment shaders are executed for all of them. And then we come to the passes of the shader. The whole shader only consists of one pass, which means we only run through the data once. The pass goes from line 49 to 67 and is what draws the outline of the object. The color and shadow itself is made in another shader, which is being accessed through the fallback on line 72. On line 52, we have the cull front setting, and it tells the shader to perform a culling on the front-facing vertices. It means that we will ignore all the front-facing vertices and we are left with the back side that we want to manipulate. In the frag method, we apply the fog to the fragment color before returning it back. The next color, which will be explained, is the solution found for Unity's outline problem. The code was made by 2 meteorology students in 2014.
The Toon shader in this project has more or less been implemented in the same way as Unity's basic Toon shader. As you can see, we have some properties, uniforms, etc. as we had in the shader just explained by Camilla. The code that solves the problem with the traditional edge not being hard enough is found in the fragment shader of this project. The fragment shader in this case decides how the light interacts with the object. Now first we take the dot product between n and l, which is the normal direction vector and the light direction vector. These are then normalized such that they are unit vectors.
As you can see, we saturate. What saturate does is that the result of the dot product will no matter what range from 0 to 1, which is where we are able to control when the shadow appears. This is done by changing the max value, which is set to 0.1 by default. This is in the end multiplied by 1000 such that the edge appears harder rather than being blurry like Unity's shader.